Okay, thank you, Cloud Person. All right, so why don't we get started? Good morning. Welcome back. Today, we will finish up where we left off with our discussion pertaining to project number 4. And then we will spend the second session, the afternoon session, actually working on the environmental display. I really hope that you invested the time since Tuesday in going over the materials. All right, so before we begin, let's address some administrative bits. Of course, the reading is to look at the KeyStudio manual in preparation for today and for your Project 4 assignment. Also, the expectation as I remove the scaffolding, i.e. have you fish for yourself, anytime you find information relevant to your project number 4, you should be putting it in your notebook. So this is your time now to find information on your own or for yourself. Environmental display is due this Tuesday, and in a shameless plug, if you want to know a lot more about computer networking, you haven't taken it yet, I have a playlist on YouTube. I used to teach computer networking at my previous institution. All right, so that being said, when we last left off, we talked about the LCD display, the 8x2, and we said it was a lot more complex as an actuator because it involved data and latching commands onto the device. And so this is the diagram from the KeyStudio manual. And we can see here their clone of the Uno. We're using almost all of the digital I/O lines along the top edge. And so it consists of the device itself, the 8x2 LCD display, and a potentiometer. And the potentiometer is purposed with controlling the voltage so that you can adjust the amount of backlight for the device. We talked about the anatomy of a sketch, and at this juncture, I'm not going to go over this anymore. And it consists of the includes section for pulling in definitions for libraries that are useful in the program, be they definitions from so-called system libraries or from libraries and definitions that you create, like we saw with the AHA alarm. Then we have another section where we put our defines, and these are just purposed with making your programs more readable. And we also have a section for the data structures that include variables. And so one question that we had is, can we use variables? Yes, you can for things that could be defined, but the difference is when you use variables, there's overhead for your runtime image. Variables take up space, whereas number sign defines do not, because the preprocessor does a find and replace with the defined specifications. Any questions about this? No questions? Yes.
What's the DI?
That's not part of this explanation, but to answer your question, those are defined two numbers. One is for the register select, and one is for the read write select on the LCD display. And then the next section is the entry points for the program, the setup in the loop, and whatever other functions like your finding state machine and your behavior routines that you know. Okay. And so here we have the Uno Wi-Fi revision 2 on the left, and on the right we have the pinouts for the device, our LCD display. And this is one we'll spend a little bit of time on because that seemed like a bit conceptual leap, and that will address your question about pins. And so here we have the pin numbers, and these pins, as described here, each column represents the odd number signal pins for the device, and this column, this next column, the right-hand column, represents the odd number. So we have the evens and the odds, and when we count them, we number them row major from right to left. So this is pin 1, 2, 3, 4, up to 14. Now, the thing to distinguish, and this is a conceptual leap, is the signal pins for the device versus the digital I/O pins for the Arduino, because you're going to be using a digital I/O pin to feed the signal pin on the device. Now, in the example, there was a data structure, an array, and that array is populated with digital I/O pin numbers for the Arduino. And so when you wire, you want to wire it, and I recommend that you use the wiring in the example so that you use the example code quite readily. You're mapping from a digital I/O line to a signal pin. And so here, the choice of DB is to mimic the DBs describing the data bus for the signal lines on the device. And so when, for example, you reference DB0, if you wired digital I/O pin 3 on the Arduino to DB0, which is pin 7 on the device, now if your code has a digital write with DB position 0 to write a 1, you would now get a +5 volts or logic 1 set on that DB0 pin on the device. And so the DBs are the data bus, and that data bus is used to either send commands or to send data characters to be displayed on the device. And so really, really pay attention to those differences between what you wire, what is the digital I/O line on the Arduino, and what is the signal pin that gets the device to do something. Any questions? No questions? Make sense? So then, next, if we were to iterate and we said, okay, well, DB1 is physically pin 8 on the device, and that's going to be driven, logic high or logic low, by digital I/O pin 4 on the Arduino. And as we loop DB2, which is pin 9 on the device, it's going to be driven by digital I/O pin 5 on the Arduino. Likewise, digital I/O pin 6 on the Arduino is going to drive DB3, which is pin 10 on the device. Does that make sense? Any questions? So really take the time to slow down and convince yourself of this distinction between how you wire the device, what the digital I/O pin is on the Arduino, and what the respective signal pin is on the device. Okay? All right. Yes. Question.
Are these slides from 50 or is that from
These don't exist. I made them specifically for today to address some of the conceptual difficulties from last class. And so it relates to what we talked about on Tuesday, but this is entirely new. Okay. Any other questions? No? All right. And so I'm not going to repeat all of these. Then when we got to the two functions, and these functions come from the example for the Key Studio tutorial for the LCD display, we had two functions. We had LCD command write and we had LCD data write. Now these functions have a certain anatomy to them, right? Set of parts that are standard. The first part, we come in and we configure the device. What are we configuring? We're configuring whether or not we're selecting the command register or if we're selecting the data register. Because that's going to tell the board, is the sequence of ones and zeros on the data bus, is it a command or is it data? Data is what you're going to display on the LCD, the ASCII character. The command is what you want the LCD device to do. Do you want it to clear the line and put the cursor at the first position, for example? That's a command. And so here, your register select is set to low if it's a command you want to send to the device. And of course, you're going to write this command, so your read-write is going to be set low. Contrast that with LCD data write, you'll notice it's selecting the data pin. DI is high. And DI is just a variable you can use a number sign to find. And that DI is literally fed by pin 12 on the digital I/O line on the Arduino. And so I want to point out the differences, but both of these have a device configuration. You have to select what the operation is, read or write, and you have to select what the register is, data or command. Then in the next section, that's when you furnish the data. You're going to all of the digital I/O lines for the data bus, and you're setting them to a pattern of ones and zeros based on whether it's an ASCII code you want to send it, or if it's a command you want to send it. And those commands are floating around on the internet if you search for commands for an 8x2 LCD display. It's a standard protocol. And so recall, when you do a digital write on a digital I/O pin on the Arduino, it remains at that state, high or low, or plus 5 volts and 0 volts if you choose. And so you presented the data after you configure it, and then you latch that command. You say, go ahead and give it a high to low transition on that enable pin, and that's going to trigger your device to go through what's called a microprogram, and it's going to enact that behavior, do something with that data that's prescribed. Any questions about this? That makes sense? And so I want you to start looking at the general structure of things, not specifically just the individual, what does this line say? Okay? All right. So this is the write command, and this is the read command. They're similar. The only difference is the device configuration between the two. Everything else is the same. So you're going to be pulling these two routines from the example code and using it to write a behavior routine that's going to display something you specify, text, on the first two lines of our display. Any questions about this? No? All right. And so let's pivot now to the humidity temperature sensor, which is really where we left off. And rather than switch back and forth between slides, I thought it would be better to kind of have everything in one slide. Okay, and so this is the humidity and temperature sensor, so-called DHT11 sensor. And Key Studio isn't the only company that makes these things. You can get them in higher quality than this and in lower quality than this. It's driven by 5 volts, and it has a pretty generous, for the price, operating range. I won't read it off. And it's a digital interface, but this particular digital interface is triggered, and it populates an Optic, and we'll have an example of that in the subsequent code. And so it only takes a single signal. It's on the device. You'll see a plus and a minus, and that's for plus 5 volts and ground. Anytime you see minus, you can assume it's ground. And we have a single signal line, and that's what's connected to a digital I/O line. Now, it might seem kind of wonky because you're going to read out something that's real value, but it's read in using digital, right? And the underlying, if you look up in the device specification from the manufacturer, not Key Studio, they just buy it out on the street. If you look at the manufacturer, they can tell you more about how it works underneath the covers. And so this is the example wiring diagram that's given to you in the Key Studio manual. And it doesn't really matter which digital I/O line you use, but if you set up the LCD, you're only going to be left with 1 or 2 digital I/O lines you can choose from. But in all of this, it really doesn't matter which digital I/O line you use. It's just using what was prescribed in the tutorial example just makes your life easier. Okay. Any questions? No? All right. So let's jump into the code. Again, we have our include section, but in this include, you're going to include the definitions for the DHT libraries. And that's going to include the definition of the class. And you instantiate this class and make it an object in your program. And then when you trigger the read, it's going to populate instance variables within this object to pull the values of temperature and humidity. So we have some defines, and what goes hand in hand with the include of the library is we need to include the bytecode implements the functions for this library. And so this is going to come from your Key Studio library. That's what it looks like in the Dropbox folder. And you're literally going to find the library subdirectory in your Key Studio example code, and you're going to copy and paste the contents of DHT11, that whole folder, into whatever directory you specify. Your IDE put project data. You're going to locate the library's folder and copy and paste this DHT11 into that folder. And if you were to go into this folder, what you would see is a header file, dht11.h, and you're going to see dht11.cpp, the C++ file. That C++ file will contain all of the implementations of the APIs that are defined in the dht11.h header file. Now, in addition to the code, is going to be a so-called properties file. And the properties file is necessary, so don't take away the kernels of the folder, just copy and paste the whole folder into your library's directory where your Arduino IDE places all of your projects. And this properties file inside of that folder gives all the pieces of information that's needed for the IDE environment to know to compile this into a library and include it with the linker. It pastes the bytecode from the definitions with the bytecode of your program. Any questions about this? And one of the things you'll see when you compile your program after you do this, you'll actually see it list the DHT library that it's compiling, including in the definition of the runtime image for your final before state. Any questions? No? Make sense? All right. So then, of course, in our anatomy, we have the number sign defines. Now, you could absolutely put a number 4 instead of DHT11 pin, but this is a lot more readable. Okay. And then we instantiate our data structure. In this case, we instantiate an object of type DHT11, which is defined in the library C++ file for DHT11. And then you go ahead and do the usual setup. Now, of course, this is mirroring what's in the tutorial, right? It's better practice to have a while loop to wait for the serial to come online, but they don't do that in the tutorial. And then we have a couple of print loops, but that's not the important part. The important part is in the loop. So we define a variable to take or store or be assigned the return from reading the DHT11 sensor. And so here, this is the DHT.read. You're triggering the DHT runtime to go ahead and read the sensor, right, for the digital I/O. And it will give you back a status code. And if that status code says okay, and again, this is exactly the code from the tutorial, if that status code says okay, then you know that those values are valid, right? And so here, there's a switch statement, of course, to print out the status code, and it will select one of those prints as appropriate. And if you get the DHT lib_OK, which is defined in DHT11.h, which you included, then you can go ahead and make use of the humidity, which is accessed as DHT.humidity, and the temperature, which is accessed as DHT.temperature. And so one of the caveats to keep in mind here is the temperature is in Celsius. And the program specification for the project is to convert it to Fahrenheit. So you're going to have to look up that standard conversion. And that's part of the think part of the sense, think, act cycle. And so we really want you to structure this as sense, think, act. That's why we did this for the bounds case there. Okay, any questions about this? Does that make sense? Okay. So let's take a look at project prep. And I should have finished this on Tuesday, but I prefer to kind of stay longer and stuff to make sure there's no mental leaps that are not addressed. So, of course, this is going to have a lot more moving parts to it than all the other projects we've done thus far. And hopefully all that scaffolding provided about sense, think, act, behavior routines, finite state machine, and so forth, as we increase the complexity of the sensors and actuators and the think part, those are going to be very important to help you manage the complexity of those projects. And so you define all the tasks you need, you order them, what needs to happen before what, and then you collect the materials you need and assign the tasks to people in your group. Then there's really two parts. There's the hardware part and there's the software part, building the circuits, right? And that's going to be a little bit more careful than we've done before in the previous projects. Then you're going to implement and test the examples because that's going to teach you what all of this API code does, particularly when you run your routine to display on the device. The command codes are going to be really, really important to understand. All right, so then you design your behavior function. Think about what those behaviors will do. So there's a lot more planning and design for this assignment than previous. And then you're going to integrate the parts in your state machine. One of the benefits of a finite state machine is that you can assign various behaviors to various individuals in your group, and then you integrate it all at the end into a working system. Sense, think, act. Any questions about this? No questions? Yeah? All right. And so I'm not going to play this. We already saw that before. but this is the finished product, and this is what you will be building in the second session today. All right. So the purpose of today is to talk about networking. And we're going to talk about networking for the balance of this morning session, and we're going to talk about networking on Tuesday's class for the entire session. If you have not given me your MAC address, get your MAC address in while the going is good. You can't connect your Arduino to the network without a MAC address. So please get that done. I've gotten 3 as of last night. There are 17 people in the class. I really need to do that. Don't put me in a position, please. We're going to have a quiz or something like that. You're adults. I treat you that way. Please get it done. Okay? All right. So that being the case, this is Internet of Things. And we talked about a lot of things, but we haven't talked about this Internet thing. Show of hands. Who's taking computer networking? Only a couple? Okay. And so for those who take computer networking, this will probably be a little boring. You've done it before. You know this stuff. But the prerequisite of this class does not include computer networking. All right. So lots and lots of internet-connected devices have done lots of wonderful things. And in fact, one of the key areas going forward with research that is unaddressed is security as it pertains to Internet of Things. As more and more of these so-called smart devices enter our daily living, it's going to be important to think about new mechanisms for what it means to secure such systems. Amazon bought Ring, and one of the things that Ring had is a smart door lock. And the idea they're actually doing now, is that when the Amazon delivery comes to your house, I don't know how comfortable I feel about this, he or she can unlock your smart lock, slip your package in the door, and then close the door. Now, in my house, a cat or a dog would kind of run out the door, and you'd never see them again. But for some people, particularly those concerned about package pirates, there are folks that will drive around all sorts of neighborhoods looking for packages and just steal them, right? This is a solution for very many people. Otherwise, they wouldn't have spent the money on it. Another interesting application is a smart light bulb, and I tinkered with one. My daughter loves it. You can change the color, the brightness, you can have schedules for when it turns on, all kinds of neat stuff. They're expensive, but they work. The internet connectivity can be a little bit spotty because there's only so much antenna you can fit in the device. But for an early version, maybe some number of years from now, it'll be a lot more reliable. Pretty interesting. There are appliances like washing machines, and these things will monitor, fill them with liquids, detergent, and they'll monitor the level of detergent, and they'll even generate order for you. We detergent arrives from the door in the mail, right? So lots and lots of interesting applications, and these are just a very small slice of Internet of Things type of applications. So this begets the question, what exactly is the internet? Now, you're very fortunate you use it all the time. I remember when I was like about 3 years old, 4 years old, if you wanted to buy a plane ticket, you'd have to drive to the airport. At that point in Logan Airport, you could park right in front. You can't anymore. But things were much more manual. If you were taking a road trip, you'd call up AAA and they generate what are called trip tickets, or trip kits. All these different maps from the areas you're going to pass through along your route when you're traveling. It's a lot different than just punch in things. If you wanted to trade stock, you'd have to have a broker and you'd call him or her and ask them to execute the transaction. You just log into TD Ameritrade or whatever, and you just do your thing, right? So the internet has revolutionized a lot of things, and the internet is an infrastructure that provides services, all sorts of capabilities to applications. Now, it's not just a traditional application that sits on a machine and does stuff and you interact with the user. These applications are so-called distributed applications. They exist in pieces that are scattered around the network. And the whole goal of these services is to allow these application pieces to reach consensus. What reaching consensus means is that they come to a shared understanding of what the state of this data structure or the system should be. And how they achieve reaching consensus is by exchanging messages. And so when you're doing, for example, voice over IP, you send an encoding of your voice, you have to make sure that that voice, those utterances, those words you're speaking are in order, and you need to make sure if someone else is talking and is listening, that you're changing the flow of data appropriately. And so the exchange of messages is done and facilitated by this infrastructure, and it's really important to understand how this infrastructure works if you want to be effective in writing these sort of applications. And so the whole goal then of this infrastructure, it consists of certain devices, but these devices collectively present protocols and APIs that allow you to make use of these services that do all sorts of things to facilitate the exchange of messages so that these pieces of application can reach consensus in an application. Okay. And so the exchange of these messages is specified typically as a so-called protocol. And a protocol is nothing more than a message format where the values those messages can take on are associated with prescribed behavior. If you want to participate in this protocol, you must understand this message structure. And when you see these values in these parts of the message, you must take this action. And so this agreement allows the participation of things like any web browser can talk to any web server. It's because of these protocols. And what you're seeing here is a so-called protocol diagram. And how you read this, if you go downward direction, that's increase in time. And if you go across, that's a message from one entity in the network to another. And so typically in computer networking, they like to personify some of these protocols, so they talk about Alice and Bob. And so in this diagram, I'll direct your attention to the protocol diagram on the left, your left. And we have a column here for Alice, all the actions Alice takes. And we have a column here for Bob, all the actions Bob takes. Now in this, Alice first initiates the sending of a message to Bob. Now there's a special name ascribed to an entity that initiates a message with another entity. It's called a client. Bob, you can think of as being a responder. You give Bob a message, Bob will respond. The special name given to a responder entity on the network is called a server. So Alice is our client, our initiator. Bob is our respondent, our server. Alice sends a message, hello to Bob. Bob gets that message, chops it up, understands what it means, and then responds appropriately. Bob responds back with a hello. Now, in network parlance, this is called a round trip. And so we have one round trip where Alice sends Bob a greeting, and Bob returns that greeting back to Alice. Now, in between, when Bob received this message and made sense of it and returned a response greeting back to Alice, Bob did a little bit of work. And that little bit of work was Bob preparing to engage in a future communication. The purpose that Alice had with this greeting round trip by initiating it, when she said hi to Bob, was to ask Bob, do you have the resources, both in terms of the computation, the data structure, the memory, the runtime, in order to engage in a particular future conversation we're going to have? So when Bob responds back hello, Bob is effectively saying, yes, I checked all my resources, I have the budget, so to speak, in order to engage in this particular hello protocol. Okay, any questions about this? Does that make sense? All right. And so now, in this next round trip, this is where the stuff is, right? The real work. Alice says, do you have the time? Now, Alice sends this message to Bob. Bob chops up and makes sense of this message. It says, aha, time. Bob then does some work. Do you have the time? Means Bob should take out his watch, look at it, think about it, and then compose that into a response message to send back to Alice. And so again, between when Bob made sense of the protocol message, got the time, Bob did some work. And so what we see here is you initiate a message, you do some work, prepare the resources, respond back, I can participate or I can't participate. Then, do you have the time? The second round trip, okay, go ahead and do this work prescribed by this message. Bob does some work, gets his watch, looks up the time, returns back the time in that message that Alice is expecting to get back that contains the time. And Alice can be assured that it's gonna return back the time because Bob said in the response to the first round trip, Bob said, hey, I'm able to do this. Okay, any questions about this? So let's kind of map that protocol diagram onto this protocol diagram on the right-hand side, your right, and this is for a TCP, maybe you fire up your browser, you type in www.clarku.edu and you hit enter. So what's happening? Well, your browser software is acting just like Alice. It's a client. It initiates the conversation. Now, TCP stands for Transmission Control Protocol. I won't talk about all the details of that. We don't have the time. That's a networking class. And what this TCP does, it says, hey, do you have the resources needed to engage in this reliable form of communication called Transmission Control Protocol, or TCP? Now, what does that mean, do you have the resources? It means, do you have variables? Do you have the buffer space, the memory? Do you have the runtime you can initiate? Do you have the computation ability in order to guarantee what it means to participate as an endpoint server in a TCP communication? Any questions? No questions? All right. So once the server or responder responds back yes on its TCP connection response, then the client engages your browser in a hypertext transfer protocol, HTTP GET request. That's a particular stylized format that is guaranteed once your client knows that the server can satisfy its part of the agreement in this TCP protocol exchange. And so you specify the GET request with the URL, Uniform Resource Locator, and that identifies a resource on a remote file system. So this message comes into the server chops it up, makes sense of it, and says, aha, you want the index.html file that's on my hard drive. So it brings up the hard drive, reads the file to memory, returns it back as a response message back to the client. Your browser gets this message, and it says, oh, I see all these HTML commands, let me draw the requisite objects on the screen, which you then see rendered as a web page. And so it's just like the Bob and Alice case. The first round trip, you're establishing resources on the other endpoint, reaching a consensus. Your understanding is this thing has the resources to engage in that type of behavior. And then you get request. It's a structured format to retrieve a file's contents off a remote file system. It does something, loads the file, sends you back the contents of the file, which you are guaranteed it's an HTML file, and then you draw it on your screen. Okay. Any questions about this? Make sense? So once again, you establish the resources in the responder or server endpoint, and you perform work in response to that message. Okay. And so there are some key structures and components in a network to be aware of. Oftentimes, when you refer to the devices that you interact with on a network, that's called the network edge, or the end systems, or the hosts. And it's a willful decision in the design of the internet to keep all the complexity at the edges or the exchange of the network, and to make it as simple as possible for the devices in the interior of the network. Because simple things can be made to run very, very fast. And when you're dealing with gigabytes and terabytes of data swirling back and forth, you want to make sure things run very, very fast and it's not very complex. And so here we have hosts, and these hosts include devices, any type of client, and any type of server. This initiator of a message, as we talked about, and this responder of a message that we talked about. And servers can exist anywhere on the network, but for economies of scale, they often are in data centers. So you have large specialized buildings with a lot of servers packed into a small space, and I can show an example of that on Tuesday. Then you also, these edge devices or these hosts can be things like automobiles or washing machines or light bulbs, as we had talked about a little bit earlier. You also have so-called access networks, and these are where your end systems get fluid, and they provide the entry point for injecting data into the network for these end systems or hosts, or receiving data from the network. And these access networks can arise in a number of different forms. In this diagram, and this is from the most popular networking book right now, the Coaxial networking book, you have mobile networks. That's things like your cell phone telemetry. Satellite is a type of mobile. It's a little bit different unto itself, but it still is a mobile network. Cars have telemetry these days. Your typical WiMAX, your air cards, as they're called, for your laptop, to access data from the cell network. You also have home access networks. This is the domain for products like Spectrum Internet or Verizon Fios product or Comcast Xfinity and RCN. There's all sorts of types of access networks for home. And typically, when you connect to the internet from these types of access networks, you're given just a single identifier called an IP address, Internet Protocol address. And this IP address is often shared among all the devices in the home, and you, through your router device, and I'll explain a little bit more what I mean by that, you're sharing that single IP address, that single address on the network among all the devices that are in the home. And then you also have your access media. Now, the access media can be so-called unguided, that's typically wireless, because that radio frequency energy is going in all directions in the air. And so when you take your cell phone has a little microwave antenna, and it's propagating this electromagnetic energy or radiation in all directions, and that's how the cell travels. And if you've ever gone on, say, a road trip, you're driving, you try to use your cell phone, it's getting really, really hot. Well, what's happening is you're too far from a cell tower, and in order to better reach the cell tower, your phone is boosting energy, and the consequence of boosting the amount of voltage of current to drive that antenna. In those cases, is that you're going to get less. Okay. And so this unguided media, like things like wireless, and so-called guided media, those materials that propagate your signal travels in the direction of that medium. So that's things like twisted pair copper wire. And if you look in the back of these little consoles here, you see green wire coming out. That's Cat 5 or Category 6 wire, so-called twisted pair, because it's copper wire inside that's twisted for various reasons. The other type of guided media are things like coaxial cable. I'll have a picture of that in a slide or two, as well as fiber optic communication lines. And fiber optic is a piece of polymer and glass, and you use light signals to encode your signal energy. And so, lastly, we have the so-called network core. The network core is the domain primarily of your internet service providers. You have two types of ISPs, regional ISPs. Those are the ones that typically deal with average business or residential customers. And then you have global ISPs. The global ISPs don't like to deal with individuals. They like to deal with large organizations. And the reason for that is these global ISPs, they generally usher signal information over long haul types of trips. And they traffic typically in terabytes or terabits of information. And so if you want to call up a global internet service provider, they're going to charge you tens of thousands of dollars a month for terabytes of data. They don't want to, or tens of gigabits. They don't want to deal with a 100 megabit connection because you want to, watch Netflix or things like that. Okay, any questions about this? Does that make sense? Yeah? All right. And so this internet is literally an interconnection of different networks. So what exactly is a network? A network is nothing more than a bunch of devices, hosts, and routers, and so forth, that communicate with one another without having to store and forward messages. They're directly reachable to one another. And so what this internet is a connection that takes a directly connected set of devices and allows you to push that information to another set of directly connected devices. And that's the internet part of it. Now, I mentioned the store and forward. The store and forward is a behavior that is performed by a so-called router. And that's the router's job to take a message, make sense of the addressing information, and depending on what that address is, it's going to send it out some link. So you initiate a message here on the mobile network, it gets stored and forwarded across different routers, and then eventually makes it to a data center that then satisfies a request, and you get back your Netflix stream, for example. Okay. Are there any questions? No questions? Does it make sense? All right. So this is a so-called coaxial cable, and this came from cable TV, and we still use it on cable TV. But when they developed cable internet, someone had the brilliant idea to say, hey, can we send data upstream, meaning from the device to the network, as well as downstream? Now, in the beginning, it was only downstream. You were getting your video content, your TV content, from the data center, from the provider, to your set-top box in your home. And so they took some of the channel bandwidth in this and implemented a signaling system called DOCSIS that allows you to send data upstream. Now, if you look at these packages for cable modems, you'll notice the downstream bandwidth, or rate at which you can get data, is often much faster than the upstream. And that's a consequence of just how cable modem works, right? It was initially tuned for cable. We get lots of video data coming downstream, but it was only a more recent thing to have data going upstream. Okay, and it's called coaxial because as you look at the conductors, we have one conductor, a copper braided sheet, separated by an insulator, and the second conductor, that's the signal carrying line, is in the center. They're along the same axis which they move, right? Hence the name coaxial. Now, when you have a cable modem, these cables, surprise, surprise, don't run throughout the country. They only run the last quote-unquote mile, meaning once you're in an actual vehicle. If you ever drive around some neighborhoods, you see these mysterious green boxes, right? Those are so-called dual pairs. And what cable companies use is fiber optic. Why? Because it can more efficiently transfer data over long haul distances. But inside of these cable headends, you have the translation to get from pulses of light, or ones and zeros, to electrical energy on coaxial. And it's the coaxial cable emanating from these head-end devices that serve the individual houses. And so if you have a cable modem type of internet residential setup at home, or parents' home, or wherever, a friend's house, and you look in the basement somewhere, you will see your cable box, and you'll see this coaxial cable emanating from them. Now, one of the other things why they use coax, it's cheap. It's absolutely dirt cheap to run this. And you typically will serve a few hundred to 1,000 homes off of one cable header. But the drawback of coaxial cable, because it's a conductor, if you stretch it out long enough, you're going to get lots of interference. And you're also it's going to act like a big resistor. And when it acts like a big resistor, what's going to happen is that voltage is going to get dropped. And now you don't get a very stable signal. Any questions about this? So this is just an example of just one type of guided media, fiber to the cabinet, the head end, and then coaxial cable, this, from the head end to the homes in a residential area. Now, you don't want to walk around and open these up, right? That's a really, really bad idea, especially after 9/11. Interfering with communication systems is the domain of anti-terrorism laws. They don't want to mess with these at all. If someone's working on it, you can stand back and say, hey, that's interesting, but don't open them. Okay? All right. So this device, I'll direct your attention to the upper right of your screen that you're seeing. This is a device that you might buy from Best Buy or a department store for between $100 and $300, depending on the features that you're interested in. And you might call this thing a router, right? But that's not a router. Routing is something very specific. Does it perform routing? Absolutely. But it has a lot of other stuff in it that you learn in your networking class. Now, this also has something called a switch in it, in this device. And a switch, singularly purposed, is on the upper left-hand side. And a switch is an active device, and it allows you to easily connect your devices in a network using cables such that you have no so-called collisions. Meaning that when two are trying to communicate with someone, one doesn't have to back off. Oh, you have the error. that allows you to have much faster wired communication. Because there's less collision. And now, if you're dealing with a data center, a rack-mounted form factor for a switch looks like this lower left. And depending on the environment, there are certain enterprise-grade switches they use at a place like Clark that allow you to perform the same action as cell phones do when they're switching from tower to tower, namely roaming. So you can have your laptop out and walk around the building, and these access points are handing you off from one access point to another. So when you buy a so-called enterprise-grade routing device or access point, what you're paying for is all of this management software that facilitates this dynamic handing off. Okay. And so this routing device, I mentioned router, and a router is the glue, so to speak, that facilitates the passing of messages from one directly connected set of devices, one network, to another directly connected set of devices, meaning another network. And so when you look at the structure of a network, we talked about the access network as providing the connectivity for our edge devices or hosts, and these access networks maintain a connection to an internet service provider. Now, managing the access networks are typically regional ISPs, and they like to deal with customer support. If you're dealing with global over long haul, all you care about is terabytes of data. You don't care about some of these networks. And so these regional access networks typically get their connectivity from a global ISP. So just like how you buy subscription, you're leasing bandwidth, they're also leasing bandwidth, but they're dealing with a larger amount of bandwidth because they're aggregating all the data from a set of mostly residential and commercial customers. And so it's a pretty good business to get in, and competition in the marketplace being a thing, if you're going to have one global ISP, you're going to have a lot of competitors. And there are all sorts of specialized ISPs for all sorts of things. There are ISPs that might specialize in sensitive information. And so if you're a customer, maybe it's a federal agency and have a lot of sensitive information, there are ISPs that handle that specifically. And so these ISPs then have to be connected to one another. So if you're on Sprint as a global ISP, and I'm on Verizon for a global ISP, the global ISP business, I should be able to send you email and you should be able to text message me. That's facilitated by two things, something called peering links. And so they decide, okay, well, if I accept 1 gigabit of data from you per month, will you accept 1 gigabit of data from me per month? And say, yes, we will use bandwidth swaps for data. And why does it matter? Because data costs money. You have the depreciation and the maintenance of the physical equipment. You have the staff that you have to pay that maintain and run these networks. And so they don't want to give away bandwidth for free because they need to monetize it and to keep that running. And there are also something called IXPs, Internet Exchange Points. And these are typically small data centers, and they're governed by economic agreements. Maybe somebody's paying for bandwidth. For example, if I think it's T-Mobile has a deal out now where if you sign up for a certain plan, you get Netflix for free, right? Well, there's probably some economic agreement between Netflix and the data centers in the ability to send data across T-Mobile's network, right? It's never just a nice thing. Okay, so that being the case, you also have regional networks. And regional networks are sort of these medium-sized service providers. They don't deal as much as the long haul as the globals, but they don't go as small as the residential access networks. And then you have this other special category that kind of cuts across everything. And these are content service providers. These are the folks like YouTube, Google's YouTube property, or Akamai. Akamai is the most famous company no one's heard of, right? Akamai is a web caching company. And they started in the early 2000s, and they're a web caching company, and their whole business is to store content and figure out where is the best location on the network to store this content. And why is that important? Because if content is closer to you physically, it'll be much faster when you try to load it. Because not savvy folks like you, but a typical, say, Netflix customer, they don't care if Verizon is having congestion on their network. They blame Netflix and they say, this fits. I'm going to blame Netflix. So these companies, the content providers, care a lot about the speed end-to-end that it takes to send content from their data center to the hosts at the customer side endpoint. And so your Googles, your Microsofts, Akamai is a caching provider, but Disney and all those do their own content. Any questions about this? So they're acting like global ISPs as well as retail ISPs. Any questions about this? No? All right. So this is a whirlwind overview, and this map, I think this is from 2015, it's outdated by today's standards, and this is a plot of Sprint's global ISP as far as the continental US is concerned. And you can see these edges, for example, from Pennsauken, New Jersey, long hop to Stockton, California. And so each one of these is a transcontinental high-speed link, typically fiber, always fiber. And you'll see these black diamonds here. These are these IXPs, these or points of presence as they're called. They're small data centers, and this is where the sharing agreement happens, and which is why someone on Verizon can send email and text messages to somebody on Sprint. And so I don't understand all the details. You have to be in those companies, understanding what the details of those economic agreements are. But these economic agreements shape the way the data flows between networks, and it's a pretty serious problem. Okay. Any questions? That make sense? So, when an interesting link, what you see, is this doesn't just cut off. This is actually an undersea communication link, right? So absolutely, these things will span across the earth, on the ocean floor, more correctly, under the ocean floor. And one amazing example is CCOM, which I believe started, if my history is right, around 2005, 2007. And the goal of CCOM was to build high-speed fiber optic fiber optic network around the African continent, right? And so this is what an undersea cable looks like to give you a sense of scale. They're absolutely huge. There's some adults there. And they literally lay them on the seafloor. Sometimes as you get closer to shore, because you can't have a big ship close to shore, you have divers laying these things. But usually it's done with a submersible robot. And if you've ever seen this thing, I think I have a video link. This robot has the cable coming into a conduit. It digs a trench as it moves along, lays down the cable, and then scoops the dirt, debris back on top. So it's buried a few feet under the seafloor. And if you have been following the news, back in, I think it was mid-January, the country of Tonga, in Polynesia, they had a massive undersea earthquake, like a tsunami. They severed their undersea cable, and so they didn't have any connectivity for phone or for internet. It was pretty serious. You still have satellite. The satellite doesn't have very much, too much latency. All right. So that being the case, this is an example of what it looks like. And here's a depiction, an actual picture of what the ship looks like. And the robot goes along the seafloor and it lays it in a trench. Now, I don't know the information about how many miles it can lay in a day, but that's just what they use. And so this is a cutaway of a smaller undersea cable. There's the URL. And if you look inside here, these are the fiber optic strands. It's not that many. They're very high speed. Question? Okay. Yes. We don't want to mess up. We want to map the seafloor. Okay. So it's hugely expensive. Just the diesel cost would be horrific. Thank you. So these are the fiber optic strands, and they're pretty high bandwidth, very, very high bandwidth. And the reason for that is because pulses of light can travel very quickly in these fibers, and there's very little interference. And so surrounding it, because it's on the sea floor, that's salt water, the seawater, you don't want to have corrosion. So they seal it in a protective sheet. And then these silver circles, those are high tension steel wires, because you want to give it rigidity. You want to make it tough. You don't want it to snap, right? That would really stink. And then you have another resin insulator to try to make it stronger. And this copper sheet here, it also transmits power. And the reason for that is every, I think it's 1,000 miles or so, you need to amplify that light signal. Well, how do you power it? No one's going to go out there and install a battery or power source. So it's inside the cable. And so not only do you send these pulses of light, every so often you amplify them, you read the signal, and then you send it out stronger again. So it propagates thousands and thousands of miles from end to end. And so we have more tensioning cables to make it strong, and then a nice corrosion-proof, but not earthquake-proof encasing. And so this is a cutaway of what an undersea cable might look like as a type of guided media. In this case, it's fiber optic guided media. Any questions? And so this is an example, as of 2018, of where the bandwidth lies for the CCOM effort, and it's still ongoing. And if you look right around, I think, Senegal, West Africa, off the coast, Cape Verde, this trunk line here, going off to Brazil, is 72 terabits. That's alarmingly fast. 72 terabits, a terabit is 1,000 gigabit, which is 1,000 megabit. So imagine 72 million megabits per second. That's a lot of data. And as you can see, there are various ports of call, and then I know wireless is really big in Ghana. I can't talk about the other countries, not as familiar. But that's CCOM, and that represents around the continent 17,000 kilometers, which is roughly 10,000 miles. To give it a more casual understanding, it's like driving from here to California 3 1/3 times, going a third of the distance. That's a lot of distance. So I can't imagine, I know it took at least a decade to do when they brought things on. Okay, any questions about this? Yeah? So yes, they use terrestrial lines and not satellite, because satellite is hugely expensive and it's very high latency. The ping time, the amount of time it takes to send a message and get a response without any data is really long, unacceptably so. Okay? All right, any questions? No? All right. And so let's talk about what these routers do. A router is a device, and its sole purpose in life is to take data that has been chopped up into standard size chunks called packets to interpret the address where they are supposed to be sent, and then store them, evaluate them, and forward them. And when they forward them, then inbound from one network set of directly connected devices to another network, another set of directly connected devices. And so when you initiate a communication at your endpoints, be that a client or a server at the network edge, you don't just send the data, you send it in these chunks called packets. And so if you're doing Zoom, for example, it looks like a video to you, but it's really 4096 in current TCP/IP, 4096 bytes at a time worth of data, and it's up to this TCP to assemble it into the video at the destination endpoint. And so its data messages, as they're called, are broken into smaller chunks called packets. And in the Carosa-Ross textbook, which I didn't have as a textbook of the course, they mark that as being of size L many bits. And then when you take these packets, they're just a sequence of zeros and ones, binary. They're encoded and put into the network as a form of signal. If you're talking about copper wire, it's going to be one of two different frequencies of that voltage. One frequency represents 0, another frequency represents 1. If it's a fiber optic cable, it's pulses of light. Pulses of light at one frequency represents a 0. Pulses of light at another frequency represents a 1. So if you have L many bits, it takes time for you to encode the first bit into signal energy, then the second, then the third, then the fourth. The total rate at which it encodes these bits into signal energy, that's called the transmission rate, or the bandwidth. That's what you pay for when you are leasing bandwidth or leasing a line for the internet. And so the so-called transmission rate, denoted by R, is measured in bits per second. And so one of the concerns in network is delay. How long it's perceived for me to say something or send data here, do you see it at the endpoint? Because delay is make or break for many applications. If you're on something as mundane as a phone call over internet, if I say hello, we're on video, I say hello, and then I say, huh, and then the LO comes like a few seconds later, you're going to be like, I have no idea what you're talking about. That's delay in action. And so one of the key considerations in computer network is analysis of the delay and enterprising to shorten or make smaller those sources of delay. And so one of the sources of delay is the so-called transmission delay. How long does it take to encode your ones and zeros for each packet into signal energy on the wire, one packet at a time? Yeah, any questions about this? Does that make sense? For those who haven't taken networking. All right. And so what this router does is so-called store and forward. In order to transmit a packet, it's not considered transmitted until it is fully arrived at the destination on the other end of the transmission. So you can have a packet that's 4,096 bytes, and if 4,095 bytes have been transmitted, but that last byte is not yet transmitted, that packet is not considered as having arrived. And so when you forward these packets, we said a router stores and forwards packets, these chunks of data, from one network to another. I'm just losing time of where I should be. All right, from one network to another. So the full packet is sent one bit at a time to the router. So the router has to have space to store it, buffer space. When you buy a router at an enterprise level, not less so at a home level, one of the things you pay for is that router memory. It's not the same as buying a RAM module for your computer. It's a lot more specialized, a lot more high performance, and you could pay anywhere from tens of thousands to 100, 150,000 for an enterprise grade router. And what the difference, many times, not always, is in the amount of router memory or buffer space. And so you need buffer space in the router in order to do this forward. And the more buffer space, the better performing your router can be because it can handle more traffic coming. Okay, and so if it takes the size of the packet divided by the transmission rate, L over R seconds, to transmit, that cost is paid for every single point-to-point connection or every so-called hop. So in this case, if you had the same transmission rate for the first leg and the same transmission rate to get signal information onto the second leg, you're going to pay twice that cost. And so if L upon R is the transmission delay, the end-to-end transmission delay is going to be 2 times that, L over R for the delay across the first leg, and L over R for the delay across the second leg. But wait, there's more, to use the infomercial. If you have data or packets, more correctly, coming into the router at a rate that's faster than the router can transmit them out, you have to store them someplace. And that's where queuing comes into play. Queuing is, of course, data structure. Yes, you've all taken data structures. That's another source of delay. The longer the line, those at the end of the line, cumulatively, are going to have to wait longer. So this idea of storing packets in a router, yeah, this has its benefits, but you don't want these packets waiting in line too long. So when you pay for the quote-unquote premium package for your service provider, what you're paying for is a preference as to which packet gets selected for forwarding when you're waiting long, right? It's the same mechanism, but you're paying for that preference, and that's how you get the increased bandwidth. So that being the case, well, buffer space, like memory, is finite. So what happens if a packet arrives at the router, needs to be stored because it needs to stand in line, and there's no more space left? Well, it gets dropped. It gets dropped. And so that's called loss. And that loss can be very, very detrimental. Because, like we saw in the previous diagram, you pay the cost of delay across 2 hops. What if you're going from, say, Worcester to Shanghai, right? And you pay the cost of a number of hops, and all of a sudden, right before the last hop, oops, the router queue is full, you get dropped. You just lost all of the delays that you paid to get to that point. And so this loss is very, very detrimental to the quality of your end-to-end flow. And so this loss happens because the data rate of packets going into the router is bigger than the transmission rate of packets leaving the router. They queue up, and it queue up enough such that you have no more space left and you have to drop a packet. And again, that choice of which packet to drop, there are many ways to do it. It can be random or it can be based on who has the premium packets, so to speak. Any questions? No questions? That makes sense? All right. And so how does it occur? Well, because the inflows are larger than the outflows. And so the packet being transmitted, well, that gets transmitted at the transmission rate, but everything else behind it is delayed. And to you, you don't say, oh gosh, what's delayed? You say, oh, my Netflix stream froze. I'm not getting any more data. There are ways to try to address that with buffering at the endpoints, but that's another conversation for another time. Okay, so the total sources of delay that can impact quality of your end-to-end data delivery are these four. There's the so-called processing delay. We talked about addresses, we didn't say a lot about them, but these addresses take time to read and process at the back. That's called processing delay. There's also the queuing delay, we just talked about. It's the amount of time that packets will line or the transmit. If it arrives at the router and there's already a packet to transmit it out the router, it has to be stored in a queue. Then the other two are transmission delay. That's the amount of time it takes to encode the ones and zeros into signal energy, right? And that's also called bandwidth, is the rate at which you transmit. And then there's also so-called propagation delay. Once your signal energy is in the communication medium, be that wired, unguided, or guided, like a copper wire or fiber, it's going to take time to physically move along that medium, right? And so a lot of people, very experienced in networking, get these two wrong. Transmission delay deals with the encoding rate. Propagation delay is how long it takes the signal to go. I mentioned satellite communication. I said it's very high latency. It takes a long time for that electromagnetic signal to physically go into space, reach the satellite, to physically get through that. It has a high propagation delay. And so these four quantities, processing delay, queuing delay, transmission delay, and propagation delay, impact the perceived time it takes for a message to go from the source endpoint, the client, to the responder, the server. Any questions about this? That make sense? All right. And so one of the things the router does, we talked about this address, that address, the so-called IP address, is how you identify an endpoint on the network. That IP address, when encoded in binary, has meaning, and that router takes it and compares it against the so-called router. So the two functions inside the router is something called routing, the determination of the pathways, the internet, the router, and forwarding. Once you get an address, you code it, and you decide based on that address which link to forward it out. Now, this routing part is interesting. That's where Dijkstra's algorithm comes in, a graph algorithm. These routers that are adjacent to one another, directly connected, they exchange information with one another about how much traffic is on the network. And based on that, they construct a graph, and then they find the shortest paths in that graph and use the result to decide which output a particular address, destination address, a packet should be forwarded through. Okay? Are there any questions about this? Make sense? All right. Well, to those who've taken network, a lot of sense, but those who haven't, maybe a little bit different. I'm kind of doing some smatterings of networking to give you a little bit of exposure to some of the underlying components. Now, in the earlier days of networking, this 7-layer ISO model is just there for history's sake. It's largely defunct because the session and presentation layers that deal with things like checkpointing and encryption, it was decided they're better left as details in the application. And so this is the modern internet stack, 5-layer. Physical layer refers to the hardware. The link layer refers to protocols for how you transfer data between directly connected endpoints. The network layer talks about the addressing and the forwarding between networks. Transport layer talks about reliable end-to-end delivery, because packets can also take different pathways through the internet. How do you reassemble them in the correct order to make or reconstruct the original message that was sent by the sending client? And then the application layer is your typical applications, like your web browser, Netflix, Skype, Zoom, things like that. Okay, so with that, I think that's my last slide. It's now 12, 11, 4 right, which is time. So we'll end there, and we'll pick back up later. The next minute, I was going to say about this one, yeah. At each layer in our software stack that gives behavior to the network, it includes data that's meaningful to other such layers in the internet. And so at the application layer, it's called a message. Go to the transport layer, which is responsible for reassembly. There's other header information that's meaningful in the reassembly of data. The network layer adds its other special piece of information that means something to routers, and it's called a datagram because it has what's called network header, the network addresses. And then the link layer for transferring across directly connected devices. In a network, it adds so-called frame information, and then it gets transmitted as signal energy to the physical layer, and it gets to another router. This switch is a pass-through that pays attention to network-specific information, not intranet or internet specific. When a router sees this message, it takes the address information, the header, it decodes it, and based on the routing tables, decides at what link it should send it. It recasts the network address, depending on where on the new network it should go, sends it back down, it arrives to your destination, and you see a web page drawn on your screen. So we'll end there, and we'll pick back up at noon with the LCD environmental display. And so hopefully this whirlwind tour of computer networking provides you enough substance so that when we talk about applications and APIs for using TCP/IP, that you can at least kind of think in the back of your head, the router is doing this. Okay? All right, any questions about this? No questions, that makes sense? Especially to those who haven't taken networking? No? All right. So we'll end there, and we'll keep it moving, especially on a nice, warm, sunny day like today. I'll see you all at 12 noon.